Hello, we are going to move forward and start discussing the second chapter where we're going to start doing less calculations but a little bit more concept. We are going to start by discussing what elements are. And if you either go in your textbook or if you Google a periodic table, you're going to get a print. It's useful to have a printout of a periodic table. In the periodic table, you're going to see roughly 119 elements, give it a take, depending on which periodic table you obtain. Those little symbols that you have in those little squares, they are called elements. So a periodic table is composed of like roughly 119 elements. Everything in the world, it's made out of elements. Everything that is matter, anything that you touch, yourself, your body is made out of elements. What elements are, it's a pure substance that cannot be broken into simpler substance. So you do not break it. They are very, very small. So elements and atoms sometimes are those two words are interchangeably. Atoms are like the tiniest units inside those elements. And the reason why they're interchangeable is, for example, if you look at carbon, capital C, that's the element, but inside carbon, you only have carbon atoms. So they use those two words. So don't let it confuse you. They basically are that that element and atoms are just composed of one pure substance that you cannot break apart. Well, for now, later on, you're gonna see how we actually can break it apart. But physically, you cannot break it apart. Now, each element is going to be identified by one or two letters. So, for example, you can have a capital C, which represents carbon, or you can have a capital L and a lowercase I, which represents lithium. I highly recommend that you memorize the first 50 elements, the symbol, and the name. Obviously, there will be no 100% that I can test you that you have memorized this, but it's going to be very useful for you to just know those elements because you're going to be using them a lot. These elements are arranged in the periodic table. They are arranged based on atomic number, and the atomic number is the one that you're going to encounter at the top of, for example, if that's an element like hydrogen, that number 1 is called the atomic number. And they are arranged based on increasing atomic number. And I will explain later on what that atomic means, the atomic number means. The position of where that specific element is, it has a lot of meaning because it's going to kind of tell you what kind of chemical properties you're going to have. For example, on the left side of the periodic table, you're going to have your metals. And on the right side of the periodic table, you're going to have your non-metals. So it's important for you to understand the location will tell you a lot about a specific element. Here we have some symbols, so you can start recognizing them and start memorizing them. You have, for example, symbols that are only going to have one letter. If that symbol only has one letter, that letter will be a capital letter always. For example, C stands for carbon, N stands for nitrogen, F stands for fluorine, capital O stands for oxygen. There will be other elements that are going to have two letters. When that is the case, you want to make sure that the first letter is a capital letter and the second letter is a lowercase letter. For example, capital C and lowercase o, it's cobalt. We also have capital Ca, which is calcium, capital A, but lowercase l means aluminum, and you have magnesium. So this gives you an idea on how you're going to represent it. These are the most common alone. That's why I told you to memorize the first 50. You're gonna see them a lot You have bromine. Notice that if you do capital C and capital O, that has a whole different meaning. That capital C and capital O is no longer an element, it's actually a molecule, a compound. So you do not want to do both letters to be capitals. So this is something familiar that you want to start probably making index cards so you can start kind of recognizing these elements, because when your exam comes as you go, you're going to see them a lot. And if you sit in there trying to figure it out what it means, especially when we get to naming, you're going to waste a lot of time and not perform as well as you desire. So please, please, please start memorizing your elements with the name, symbol, and atomic number. Here we see a more a periodic table, a modern periodic table. There are some really old ones that look completely different than this. But what you're going to see is you're going to see 7 periods. So these are going to be your horizontal rows. And the way you start is from the left to the right. That's how you read it. So you have 7 periods. Now also you have 18 rows, which are vertical columns. So you have 18 columns, sorry, yeah, 18 groups, which are vertical columns. So we call them 18 groups. So this will be group 1, group 2, and so on. And we have 7 horizontal rows, which are called periods. Those are on your periodic table. Now, the way we classify, we have different ways of classifying the periodic table. One way of classifying the periodic table is by dividing it into 3 different groups. Everything with the exception of hydrogen that you see in green, all of these are your metals. Oops. Your metals. All of that is metals, which means that the periodic table is mainly composed of metals. Anything in blue are your non-metals, non-metals. And we roughly, I believe we have like around 19, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. Okay, I thought it was 19. Maybe I missed something. So those are your non-metals, which means they can be a gas, they can be a liquid, and we'll discuss that a little bit more further. The ones in orange here in the center, which is like a zigzag, those are your metalloids. What that means is that those specific elements are going to behave like a metal, but it's also going to behave like a non-metal. So it's kind of like in between. Now, notice the numbering. I'm not sure if you've noticed the numbering. The numbering, it's changing here, right? So we have group A and group B. So that brings me to the second way of dividing the periodic table. We divide it into main group and transition metals. So the main group, let me get a different color. The main group will be the A group. That will be your main group. So this is another different way of dividing the periodic table. The transition metals will be the ones in the center. These are called transition metals. And we'll get to it. Just want to kind of introduce you that we can divide the periodic table into in different ways. For example, I can divide you by being a teenager, or I can divide you by saying you are a 6 foot person, or I can divide you by different categories. It's just different ways of dividing the periodic table. You have learning checks that I also often put in between my slides. They are very useful, so try to do them without looking at the answer. So for example, here, I will practice a couple of times and then try to see if you can answer these questions without looking at the periodic table. For example, they're asking you for the correct symbol of iodine, and you will know that it's capital I. Iron is Fe. Magnesium, zinc, and lithium. So usually when I give you this, I'm also going to give you the answers. Um, but it's very important that you try to do it on your own. Oh, wait, that's the opposite. So magnesium, zinc, and lithium. The other learning check is asking you to actually write the name. So P is for phosphorus. R, AR is for argon. This is for manganese, beryllium, and potassium. So notice potassium does not, it starts with P. The symbol for potassium is not P, it's K. So going back on the way we were discussing of dividing the periodic table, the first way we have metals, metalloids, which in this case are in purple, and non-metals. So for now, we're gonna go over these properties um, of each of these different groups. So metals, non-metals, and metalloids. So metals, it's they're going to be on the left of the periodic table. Most of the periodic table is composed of metals. They are good conductor of heat and electricity. The reason why metals are good conductors is because they like to get oxidized. They like to get oxidized. What does that mean? It means that they like to give electrons. They like to give electrons. And electrons. And keep in mind that electrons have a negative charge. So think of charges, negative charges floating in the solution. So when a charge is floating in solution, something can conduct heat or electricity. That's why metals are considered good conductors. Metals are shiny. I'm sure you've seen like gold and platinum and all of that. Those are shiny at room temperature. They're also solid at room temperature, with the exception of mercury. Mercury, it's a liquid at room temperature. Non-metal, on the other hand, which we have that right side of the periodic table, they are going to be dull. They're not going to be shiny. They are poor conductors. The reason why they're poor conductors is because they like to be reduced. They like to be reduced. What does that mean? That they like to gain electrons. They like to gain electrons. Non-metals can exist as a gas, solid, or liquid at room temperature. So there's nothing like specific, like, like metals, no. You can find them in any of these states. Examples that they give you here is, for example, sulfur and carbon at room temperature, they're found as solids. Bromine is found as a liquid at room temperature. Nitrogen and oxygen is found as a gas at room temperature. Metalloids, on the other hand, are the ones in the center, the zigzag that we went over it. They have properties of both metals and non-metals. They are they're intermediate. So here are the 7 metalloids that I recommend you memorize: boron, silicon, germanium, arsenic, antimony, selenium, and astatine. So it's very, very useful if you memorize these metalloids. Now, why do we care about this element? Well, I told you that these elements compose everything in the world. For example, we actually have 4 elements that comprise of 96% of your mass, or your human mass. And those elements are oxygen, carbon, hydrogen, and nitrogen. Those are found in your biological molecules, which are your proteins, your carbohydrates, your lipid, your nucleic acids, which they compose your DNA. So they are very, very important. So those are the four elements that pretty much take care of 96% of your body mass. Okay. We also have major minerals. These are elements that are present in smaller amounts. At least 100 milligrams of each is needed in your diet. So you need this, such as magnesium, sulfur. The reason why you need them is because they are found in your protein. So it's very important for you to have. We also have other traces of elements, which means less than 50 milligrams, such as iodine, which is needed for your thyroid to function correctly. Here we have just kind of an image of what I just said, how your body needs all of those elements. There's obviously other things, but this is the major ones. Here we have a practice problem that you guys should pause and try to answer on your own. Moving forward, now we're going to start discussing compounds. What the reason most elements do not exist by themselves. For example, you're not gonna find hydrogen by itself. You're actually gonna find it at H2, or you can find it with a combination of other elements such as oxygen. So because they're free rare, they're always going to exist together with its own or with other compounds forming a compound. So with other elements forming a compound. So compounds are pure substance formed by chemically combining with two or more elements in a fixed ratio. A chemical formula consists of an element symbol to show the identity of each element forming a compound. The subscript that you see here indicates that you have two hydrogens. So every time you have a ratio 2 to 1, 2 hydrogen to 1 oxygen means that you have water. For example, in here indicates that you have 3 carbons and 8 oxygen. Sometimes you will see this and you will see a subscript outside. Well, that subscript, that 2, is going to correspond to carbon and oxygen. So if I ask you how many carbons you have, you will say 2 times 3 will be 6. How many hydrogens you have? 8 times 2, you will have 16. That's how that subscript, if you see it later on, that's what that means. In chemistry, usually we use colors to identify a certain element. You don't have to memorize this, but it's useful to recognize that for us, black means carbon, white means hydrogen, and so on. We're gonna learn later on in this drawings, but notice in here the oxygen is represented in red, and these two little white balls, it represents hydrogen. So if we ask you a question like this, which one will be a compound versus which one is an element? I don't know what happened to it, please. Okay, so note here, because here it's one element, two elements, three elements, this will be considered a compound. This also is a combination of two different kind of elements. It will also be considered a compound. This is only helium, so it's just one element. it's a silver element, and so on. So this should help you identify whether you are dealing with a compound or whether you are dealing with a element by itself. The reason, quick, I don't know if I mentioned this, this is actually going to be considered a molecular element, because it has two of its own. So sometimes they're also called diatomic elements. Diatomic meaning they like to exist as two, and we're actually going to have 7 of them. So this is considered a diatomic element, sometimes called molecular element. Now we're going to start discussing the structure of a proton. In the center, the proton, the atom, in the center, there will be a nucleus. In the nucleus, you're going to have protons and neutrons. The protons are going to carry a positive charge, and the mass is 1 AMU. AMU is the unit that we use. The neutrons are going to be considered a zero charge, zero charge. So protons and neutrons are located inside the nucleus. Outside the nucleus, we have like what is called like electron clouds. In these electron clouds, we're going to locate the electrons, which carry a negative charge, and A has a 0 AMU, and the nucleus has 1 AMU. So nucleus, it's where you have your protons and your neutrons, is the heaviest part of the atom, because those the protons and the neutrons have mass. The electrons, even though have mass, is very, very small, that we say has 0 AMU. The electrons are basically in this cloud, empty space, and they carry a negative charge. So here's a summary. Electrons carry a negative charge. The mass is so small that we neglect it. We say 0 AMU. The number of electrons determine if the number of electrons of an atom determines the chemical behavior of the atom. So even though the electrons are very, very small and they don't really have a mass, they are going to actually tell you how that atom is going to behave. So it has a lot of power even though it's very small. The protons are going to be located in the nucleus, and they are going to carry a positive charge. They are way larger, like 2,000 times larger than an electron. We say that they have 1 AMU for mass. The neutrons are located in the nucleus. They exhibit no charge. They're roughly the same mass as the protons, so we say they have 1 AMU. Neutrons plus the protons equals the mass of an atom. So for example, if you look at the number that is located below the symbol, that will be the atomic mass. And the atomic mass, it's going to be the addition of the neutrons plus the protons. So this gives you a summary of the entire three subparticles we were talking about. So we have the atom. Inside the atoms, you have a proton and a nucleus, which is located, a neutron, which is located inside the nucleus in the center. The proton carries a positive charge, the neutron carries no charge. In grams, this is the masses, which we're hardly going to be using at all. We're not going to be using at all. We're going to be using this. So as you can see, for protons, we use 1 AMU. For a neutron, 1 AMU. And for the electron, we say it's pretty much 0. It's very, very small. One one idea that I want you to think about is that opposites attract. So protons are going to this cloud. Remember how I told you that here's the nucleus and here you're gonna have your protons. In this cloud is the electrons. And the reason why the electrons like stay there is because there is an attraction between the protons and the electrons. This attraction is because they don't, one is positive and the other one is negative. So there is that attraction. When you have two particles with the same charge, they're going to repel because they have the same charge. But when they are opposite, they're going to attract each other. So there is an attraction between the proton and the electrons because they have opposite charges. Here's a study check that I recommend you pause it and you try to answer it. Located outside the nucleus, the electrons has a positive charge, the proton, has mass but no charge, the neutron. Moving on to the atomic number, which is located here. Now, something very important that you need to memorize is that the proton equals the atomic number. Protons equals atomic number. And that is unique for every element. No element has the same number of protons, which means that if I tell you I have one proton, which element am I? You look at the periodic table and you look at which atomic number one, and you're gonna see that it's hydrogen. If I tell you I have three protons, what element am I? You're going to look at the periodic table. You're going to look at the atomic number that is number three, and you're gonna see that you are lithium. So the protons are unique. No element has the same number of protons. So every time I said three, you should be thinking lithium. Every time I say six, you should be thinking carbon. Every time I said five, you should be thinking nitrogen, and so on. Net charge. So sometimes there will be elements that carry a charge. And what's gonna happen is the way you're gonna do the charge, it's going to be, so protons equals electrons, that means that the charge is zero. So if I have, for example, carbon, if I say you have 6 protons and 6 electrons, that means that the charge is zero. Now, how do we calculate the charge? The charge, it's, the charge, let me see which element I want to do. One second. Sorry, I'm trying to get to a periodic table, but it's not letting me. How many windows open? So for example, the charge is going to be equals the protons minus the electrons. So if I said that I had if I have fluorine and the atomic number of fluorine is number 9, which means that it has 9 protons, 9, and I have 10 electrons, that means that the charge would be -1, and the way we represent it would be F -1. But if I said that I have fluorine and this fluorine has 9 protons and it has 9 electrons, that means that in this case the answer is 0, and we just represent fluorine without a charge like that. So that is the difference. Notice one has a negative charge and one doesn't. So you always want to remember, in order to calculate the charge, you want to use this equation. Okay, so as you can see, the atomic number, we're going to use Z to represent the atomic number. So lithium, the atomic number is 3. What that means is that it has 3 protons in the nucleus. Every atom of a given element has the same number of protons in the nucleus. So no matter if so the reason why this statement is important is because we're going to be talking about isotopes. So isotopes is an element that has the same number of protons but different number of neutrons. So what basically this is saying is that if you're talking about lithium, no, it will always be the same number of protons. That's never going to change. Different elements have different atomic numbers because every element has a specific number of protons. So remember, protons equals atomic number. A neutral atom has no net charge, so the Z is going to be protons equals the number of electrons. So that's why it's 0, because if you have something with no charge, so for example, if I tell you I have lithium without charge, that means that lithium, you already know, because Li is 3 atomic number is 3, that means it has 3 protons. And because there is no charge, it has 3 electrons because they have to cancel out. But if I tell you Li plus, that means that it still has 3 protons. Okay, it still has 3 protons, but now it has 2 electrons. It has 2 electrons. Okay, if I tell you oxygen versus me telling you oxygen -2. So if I tell you oxygen, that means we're talking about number 8, right? So that means that it has 8 protons. This one has 8 protons and 8 electrons. However, this one, it's going to have, so how do I know how many electrons I have? So remember that I told you that the charge equals protons minus electrons, okay? So we know the charge is -2. We know the proton because the proton is never gonna change. It's gonna be A minus E. So the way we're gonna do it is we solve for E. And in this case, you're going to have that you have 6 electrons. You're gonna have 6 electrons. Okay? And I can do some more practice if that's not clear. Here we have the symbol. This is how we represent chemical notation, the symbol, the atomic mass, the atomic number, or the mass. Learning check. Select the correct number of protons for each atom. So if I'm talking about fluorine, you're going to look at the periodic table and you're going to see that fluorine's atomic number is 9. So select the correct number of protons for each atom. So if you look at, for fluorine, if you look at the periodic table, Fluorine should be number 9. So I don't know why the answer is not here. It should be 9, not 7. It should be 9. I don't want to confuse you. Potassium, if you look at the atomic number, potassium should be 19. Barium, if you look at barium and you look in the periodic table, you should see that barium should be, where is barium? Yeah, barium is number 56. That means that it has 56 uh, protons, sorry, 56 protons. Yeah, so here's the answer. I don't know why they put 7 in the other one. It should be 9. Okay, atoms are neutrals. An atom of any element is electrically neutral. It has 0 net charge. So if you see something like carbon and you don't see nothing as a superscript, that means the charge is 0. What that means is it has the same number of electrons as the same number of protons. Remember, protons are positive, electrons are negative. So if you have that same amount, they cancel each other. A neutral atom of calcium, for example, has 20 protons and 20 electrons. So calcium like this has 20 protons, P, 20 electrons, E. However, if I give you calcium 2 plus, and I ask you, and this is in the quiz or test, if I ask you how many protons, you're going to say 20. And if I ask you how many electrons, you should be able to tell exactly that it's going to be 18. But if you don't know, the way you're going to do it is charge equals proton minus electrons. So in this case, the charge is 2 plus, right? So the charge is 2 equals protons, you know it's 20 minus electrons. So this should be minus 20, minus 20. So then you're going to have negative 18. And then divided by the negative, you're going to have 18 electrons. 18 electrons. Okay? Here is another really good question that I would like you to do. Atomic number. So you're going to have a periodic table in front of you. You're going to have something similar to this. So try to do it by yourself before looking at the answer. Here's your answer. I hope you got it right. If not, try it again. So here's a study tip. This is something that I would highly recommend to practice this slide. Number of protons equals the atomic number. Protons plus neutrons equals the mass, also called atomic mass. Number of neutrons equals the mass number minus the atomic number. Mass numbers apply to specific atoms of an element. I have another learning check. So if I give you lead and it has a mass number 207. So the fact that I give you lead, this should tell you the atomic number. And because if you look at the periodic table and you look for PV, it will tell you the atomic number. And you have to remember that the atomic number equals proton. Okay, so try to answer those questions. I also want to give you that the mass number equals protons plus neutrons, okay? So notice here, they gave you, you already know the protons because you know what PV is. And from there, you have the mass number, which is 207. You can calculate the neutrons. And then from there, since it has no charge, the number of electrons equals the number of protons because it doesn't have charge. So try to answer by yourself, then move on to the next slides where you're gonna locate the answer. I have another learning check, same idea. And an atom of zinc has a mass of 65. So if it has 65, how many protons are in the nucleus? So notice, remember that the mass equals protons plus nucleus. Remember, the fact that you know zinc, that means you know how many protons, because zinc, if you look at the atomic number equals to proton, and so on. So how many, so if you look at zinc is going to be, I think it's number, I'm gonna write it down. Zinc is going to be number 30th. So number 30, so if you look at zinc, that means you have 30 protons. And then you have 65 being the mass plus N. So they're asking you how many protons. The answer for this is going to be, wait, how many protons? Zinc. Zinc is number 30th. Why do they don't have 30 here? Am I correct with zinc? Yeah, zinc. Yeah, zinc is number 30. Oh, yeah, here it is. Am I blind? It's number 30. So that means that that's that answer. How many neutrons? Well, you do 65 minus 30. That will give you the answer, because remember that the mass proton equals protons plus neutrons. So if you do 65 minus 30, that should give you the number of neutrons, which is 35. What is the mass of zinc atom that has 35 neutrons? Okay, so if it has those 35 neutrons, so that means that the protons are never going to change. The protons are always going to be 30. So 30 plus 37, that should give you the answer, which would be 67. And let's see if I got it right. Yep. So here it is. Here's another one. So it says 14 protons and 20 neutrons. So look at the periodic table and look at atomic number 14. That will tell you which element we're talking about. So what is the atomic number? It has to be 14 because protons and atomic number is the same thing. What is the mass number? 14 plus 20 should be 34. And based on that, whatever element you came out with, that will be the answer, which was silicon. Okay, we're gonna start talking about isotopes now. Let's move on and discuss isotopes. Isotopes are gonna be atoms or elements, remember, that have the same number of protons, but they have a different number of neutrons, which means that the mass is going to change. For example, because the mass number is the number of protons, which never changes, plus the number of neutrons. So in here, this indicates the mass. The 35 indicates the mass, the 37 indicates the mass. Well, chlorine will always be 17 because that's the atomic number. So in this case, that if we do 35 minus 17, we know that we have 18 neutrons. For this one, if we do 37 minus 17, we have different neutrons. These two are isotopes, and we call them chlorine 35 and chlorine 37. They are isotopes. We have two different isotopes here of sodium, mass 23, mass 24. The number of protons is never going to change. If we do 23 minus 11, we'll have 12 number of protons. If we do 24 minus 11, we will have 13 of neutrons. So this element has 11 protons and it has 12 neutrons. This sodium has 11 protons and it has 13 neutrons. Okay, what if I ask you how many electrons? What if I said this is plus and this doesn't? This one, since it doesn't have a charge, is going to have 11 electrons. But this one, since it has a charge, is going to have 10 electrons because it gave one up. So make sure that you guys understand this topic because it's going to come back. A certain isotope contains 23 protons and 28 neutrons. What is the number? What is the mass number? Well, all you need to do is 23 plus 28. That will give you the mass number. And then what element? We'll look at the periodic table and see that atomic number 23. When you look at 23, you're going to see that it's vanadium. Learning check. There are 3 naturally occurring isotopes, carbon 12, carbon 13, and carbon 14. Write the atomic symbol of each isotope and say the number of protons, neutrons, and electrons in each of these isotopes. We're going to have a question very similar to this on the exam. So make sure that you guys understand it, since you're going to have something very similar on the exam. Okay. So they're saying that you're talking about carbon, all of them, right? So they're all of it carbon. So since it's carbon, look at the atomic number. It's all gonna be 6, okay? Now they're telling you that one is 12, one is 13, and one is 14. So 12, 13, 14. So that's the mass number. So 12 minus 6, 12 minus 6, that will give you the number of neutrons, which is 6. 13 minus 6, that will give you the number of neutrons, which is 7. 14 minus 6, that will give you the number, which is going to be 8. And in this case, since all of them have no charge, they didn't give you a charge, and we're gonna put 6 here, 6 here, 6 here. They're all gonna be 6, 6, 6. If this had a charge, so I'm gonna change the pencil because this is a scenario. If this had a positive charge, then it would mean that it gave 1 electron, so that means that they will have 5 electrons. If this had a negative charge, that means it will have 7 electrons. Just giving you a scenario. And here's the answers. The atomic weight, which is also called atomic mass or formula mass, is given in unit AMU. The atomic weight is the weighted average of masses of the naturally occurring isotopes of a particular element reported in atomic mass units. So this number that you see here is the average of the masses of all the naturally occurring isotopes. So this is the average of all the isotopes of carbon. Let's do another practice question before we dig more into that problem. Write the atomic symbol for atoms for each of the following subatomic particles. So you want to find out which one is 8, which one is 17, and which one is 47. That will give you and you want to make sure you write it like this. Another question, consider the following pair of atoms in which X represents the chemical symbol of the element. Which of the pair of isotopes are the same element? So this represents the mass, and the bottom represents the protons or atomic number. So the ones that have the same would represent the same element. In which pair do both atoms have 8 neutrons? So what you have to do is 16 minus 8, 15 minus 7, 14 minus 6, 12 minus 6, 15 minus 7, 15 minus 8, and whichever gives you the same number, that will be the answer. So it will be, this is 8 neutrons. So you want to make sure that it's going to be, 15 minus 7, that will give you 8. So it will be C. That's the answer for the first one. Answer for B. So see this, 8 and 8. So going back to isotopes, isotope is going to have an abundance, and this is percentage. So remember that this equals 100%. If we divide this by 100, we get the fraction part. So the number that you see under chlorine is the average of these two isotopes. It's the average of those two isotopes, and that's the number that you see. Notice that the way we're going to do it is we take the mass times the fraction of the first isotope, isotope 1, and we add it to the mass times the fraction of the second number. And when we add these two numbers, you get this. This is the average. This is what you see in your periodic table. And it's the average of the two isotopes that exist. You don't have to know how many isotopes exist. That's something that I'll be providing for you. A question like this you'll get on the exam. For example, it says gallium has 2 occurring. So it has 2 isotopes. One isotope and the second isotope is this. Calculate the atomic mass of gallium. So it's going to be atomic mass equals, this represents the sum. You're going to have the mass, so it's going to be the fraction of gallium 69 times the mass of gallium 69 plus the fraction of gallium 71 times the mass of gallium 71. So if we do that, we're going to do atomic mass equals, so the fraction it's going to be, you're going to do 60.11 divided by 100 is going to be 0.06011 times 68.9252 plus divided by 100.3989 times 70.9247. And when you do the math, your answer should be in 4 significant figures. You should have 69.72 AMU. You don't want to forget your units. Here's the answer below. Make sure you guys know how to do those problems. This problem will definitely be on the exam. Now we're going to go over the periodic table again, but this time we're going to divide it into main groups. The main group, which is going to be your 1A, 2A, and we skip to 3A, 4A, 5A, 6A, 7A, and 8A. The center here is for the transition metal. So we have the main group and transition metals. Within the main group, group number 1 is called alkali metals. Group number 2, and you need to memorize this, is alkaline earth metals. Group 8A is called noble gases, and 7A is called halogens. So now we're going to go over some of their properties. The main group consists of tall columns. On the right and the left, the groups are numbered 1A to A8. Your transition metal elements are the 10 short ones that are labeled short columns, which are labeled from 1B to AB. And then you have your inner transition elements, which consist of the lanthanides and the actinides. We really don't need to kind of memorize this, just be aware of it. But it's going to be helpful to know it, but if you don't, you need to know it. So notice here, this is your main groups, are the ones in blue, the transition metals, and the lanthanide, and which are the inner groups. Alkali metals and alkaline earth metals have similar properties. They are soft and shiny metals. They have low melting points. They are good conductors because, remember I told you they like to get oxidized. And on top of that, which means they like to give electrons, right? They like to give electrons. They react with water for basic solutions. When you put one of these metals with water, you're gonna see sparks, you're gonna see small fire, because they're very reactive with the water. Alkali metals are your lithium, your sodium, your potassium, your rubidium, your cesium. They are very reactive with water. They like to give away one charge. Sorry, one electron. So what that means is that they become lithium plus, potassium plus, so on. They like to give one electron. When they give an electron, they become an ion, which means they carry a charge. An ion, anything that carries that's an ion, that means it carries a charge. Alkaline earth metals are going to be your 2A. They are fairly reactive, but not as reactive as your alkaline metals. They like to give 2 electrons away, so they become beryllium 2 plus, magnesium 2 plus, calcium 2 plus, strontium 2 plus, barium 2 plus. They are going to have a low density, very reactive. They like to get oxidized, like to give 2 electrons. On the other hand, we have your halogens. They are also very active. They like to exist as 2 atoms joined together, which are your diatomic, such as your bromine, oxygen, and all that stuff. Very reactive. They like to get reduced, and they like to gain a negative charge. So they like to gain one electron, and what happens when that happens is that they become negative charge, one charge. Chlorine. Noble gases are really, really stable. They do not like to be with other elements. They're happy the way they are by themselves. So a little bit more of the halogens. They are very reactive. Remember, they like to be reduced. Fluorine, chlorine, bromine, iodine, and antigen. They are fluorine, it's a pale yellow gas. Chlorine is a gas. Bromine, it's a liquid. Iodine, it's a purple. You don't have to memorize. It's just common knowledge for you. Noble gases are very reactive. They are very happy the way they are. They usually do not like to lose or gain electrons. They are stable the way they are. Examples are going to be your helium, neon, argon, krypton, and xenon. Usually we use these gases to put them in like balloons, those signs that we see at many stores or clubs. Yes, they put these noble gases. Okay, now we're going to start talking about a specific element in the periodic table, and that is your carbon, which is capital C, that is the chemistry symbol. Carbon has the ability to join itself and other elements, and it is able to form many different compounds. What I mean by that is that carbon likes to have four things attached to it, either four carbons or four different elements. Carbon is unique. For example, graphite, it's carbon. Diamond is carbon. It's just plain carbon. The difference is the way those carbon atoms are arranged. For example, in a diamond, if I asked you for an example of an element, if you tell me diamond, that is correct because diamond is only carbon. But the way diamond, the carbon atoms are arranged in diamond, it's like crystalline way. In a graphite, it's an amorphous way. There's no pattern. You're just kind of thrown together. Notice here in this type of molecule how they arrange. So it's still just carbon. The difference is how those carbon atoms are arranged. Now, we are going to switch topics completely. And if it's a little confusing, we can talk about it and discuss it more. I don't understand why this topic is in this chapter, but let's get through it. So an electron it's in a specific region, right? We have the nucleus, and then we have these shells where you find the electrons. Well, there are going to be more than one shell. Each shell can only hold a certain amount of electrons. So if you only, like the first shell can only hold 2 electrons and it has a certain amount of energy. If you need to put more electrons than that, you need to go to the higher level. They call this the principal energy levels or shells, and we represent this by N. What that means is that this will be N1, this will be N2, N3, and so on. As you move, remember that the nucleus is this little dot that I'm going to put in the center. That's the nucleus. As you move away from the nucleus, the electron is going to have more energy. N2 has more energy than N1. N2 has more energy than N1. N3 has more energy than N2. Electrons in lower number shell are closer to the nucleus and are lower in energy. So if I ask you which electron has more energy, the electron in N1 or the electron in N3, you're going to say the electron in N3 because it's further away from the nucleus. Electrons in higher number shells are further from the nucleus, are higher in energy. Same idea. Because I'm further away from the nucleus, I'm going to have more energy. And that's what they're saying in those slides. Now, the way I want you to think about this principal energy level, it's like you're going up a ladder. As you go away, N1 is the lowest. As you go up, you're gonna have more energy. So the electrons, there's only a certain amount of electrons that are gonna be located here. For example, in N1, you can only have 2 electrons. In N2, you're gonna be able to hold 8 electrons. And I'll give you those numbers later on. But let's say you need to put 3 electrons. Well, you can only put 2 in N1. So you're going to put 2 here and you're gonna put 1 there. You always have to fill the one lower before you go up. Meaning you can skip, you can jump. You're gonna fill the one lower, then once you have that one full, you're gonna put the rest on the one highest. And 7, so you keep going, right? It's further away from the nucleus and it has more energy. The energy of an electron is quantized. What that means is that it has a specific amount of energy. So for example, just giving you, let's say this, like, let me see if I can relate it. So let's say N1 can only hold 100 calories, right? But you need to put 300 calories. So what you're gonna do is, because it's quantum size, meaning it can only hold 100 calories. So what you're gonna do is you're gonna put 100 in one, and then the rest you're gonna put it in M2. And if you have left over, you put it in M3, and so on. Now, this is how pretty much it looks. You're going to have this is the nucleus, and 5 has more energy than N1. Less energy. So N5 has more energy than N1. Now, when the electron is at N1, for example, let's say this is N1, you need to give it energy. The electron is going to have to absorb energy. We call that energy absorption. So because when here, you need to give it energy to excite it so it can go to the higher energy level. So you're going to excite it. So we call that energy absorption. When the electron is at N, let's say 3, and is trying to go to a lower, we said that there is energy that is going to be emitted, and it gets emitted in the form of a photon, which is light. So when electrons go from a lower level to a higher level, energy is absorbed. When an electron goes from a high level to a low end, energy is emitted, is released in the form of a photon. The energy emitted or absorbed equals the difference between the two energy levels. So it has to equal each other because energy cannot be created nor destroyed. Okay, learning check for what I just taught you. Hopefully it's not too much at once. In each of the following energy level changes indicate if energy is absorbed, emitted, or not changed. An electron moves from the first energy level to the third. So it's going from low to high. So it's energy is being absorbed, or energy is being released, or nothing. In this case, energy will be absorbed. An electron falls from the third level to the second, so it's going from N3 to N2. Energy is going to be released because it's going from something that has more energy to something that has less energy. An electron moves within the third energy level. So basically this is N3, the electron is just moving here. There is no energy absorption or there is no energy release. Those are the answers. Now, electronic structure. As I told you, each shell can only hold a specific number of electrons, and you're gonna have to memorize this. Shells with large numbers, which are N, are farther from the nucleus and can hold more electrons. What that means is that N4 has more energy, and it can hold more electrons. The maximum number of electrons in each shell is given by this formula. So for example, let's say you want to know how many electrons can hold in n equals 5. In n equals 5, so you will do 2 pi squared. So 25 times 2 will be 50, right? So this is how you will find out using this equation how many. So notice here, if we do n equals 2, so n, we're using this equation, so it will be 2 squared. So 4 times 2 is 8. That's how we got 8. Notice if n is equals 3, it will be 2 times 3 squared. 3 squared is 9. 9 times 2 is 18. That's how they get those numbers. So each shell can only hold a certain amount of electrons. Now, the shells are divided into subshells. So basically what I'm saying is, think of a shell being this big. Let's say that's how N2 looks. So within here, you're gonna have compartments. Those are called subshells. You can have S and you can have P. So notice here, in what they're saying, an orbital is a region of space where the probability of finding an electron. So what they're giving you is that probability where you can find this electron. Each orbital can only hold 2 electrons. This is all gonna come together later on. So notice here, it's S, has 1 orbital. So that means you can only hold 2 electrons, and we represent those electrons on those half arrow. P has 3 orbitals, 1, 2, 3. So P can hold 6 electrons. D has 5 orbitals. So D can hold 10 electrons. F has 7, so it can hold 14 electrons. Okay, so S 2 electrons, P 6 electrons, D 10 electrons, and F 14 electrons. This is how the shells look. You don't have to worry about drawing this, but notice here, this is what, here you only have 2 electrons. In the P, you have 1, 2, 3, 4, 5, 6. In the D, you hold 10, and in the F, you hold 14. Don't worry, no need to stress. You're not gonna be drawing this. You just wanna be familiar on how they look. This is the table that is very important. In N, this is your N. N equals 1. Inside your N, so let's say this is your N. I'm making it look like that. You're only gonna have an S orbital. So since S only has 2 orbitals, you're only gonna be able to hold 2 electrons. In N equals 2, you're gonna have S and P. P has 3 suborbitals and S has 2, so you're gonna be able to hold 8 electrons. Because here's your 6 and here's your 2, that's where you get the 8. In N equals 3, you're gonna be hold 18 electrons, 2 from S, 6 from P, and 10 from D. In N equals 4, you're gonna be able to hold 32 electrons, 2 from S, 6 from P, 10 from D, and 14 from F. This is P, this is S. This table is extremely important, okay? The S orbital has a spherical shape. The orbital gets larger, so N1, S of N1 looks like this. S of N2 looks bigger, and so on. It's just increasing in shape. Same idea with the P. The P has dumbbell shapes like, okay? Now, with that information that I just went over, we need to apply it and do electron configuration. Electron configuration, think of it as just being a unique address for each electron. So each electron has a unique address. The electron configuration, the formal definition is shows how an electrons are arranged in an atom orbital. So I really encourage you to read the book for this section because it can be a little bit confusing. So there are rules that we're gonna have to follow. Electron configurations I place in the lowest energy orbital. So you always wanna start with 1s. Okay, then you want to increase orbitals are then filled in order of increasing energy. So this is the way you're going to fill it. So you're going to go 1s2. That 2 right here, that 2 represents the number of electrons. Remember, in S, you can only put 2 electrons. So you can't, S equals 3 is wrong. You cannot put more than 2 electrons. Then you go here. The arrow is telling you where to go. 2s, you're not gonna have this table, so you need to know how to memorize it. 2s2. Then once that is filled, you're gonna go to 2p, and remember in p you can only put 6. Then you go to 3s. So let me give you an example. Let's say I ask you for the electron configuration. So the question, so if you know how to draw this diagram on your blank piece of paper, you'll be okay. Let's say I ask you for the electron configuration of, let's say fluorine. Isn't fluorine 9? The atomic number, I think fluorine is 9. Yeah, it should be. I know it. I know why I'm like, not remember. Okay, so that means you have to account 9 fluorine, and since it doesn't have a charge, that means it has 9 electrons. So if I ask you for the electron configuration, you start at the bottom, so you have to distribute 9 electrons. 1s2, so now you have 7 left. Then you have 2s2, you have 5 left. And then, so you have 2p, you don't need to put the 6, right? You only need to put 5. So this is the electron configuration of fluorine. So you just keep adding 1 electron and you follow this pattern on how to correctly do the electron configuration. So if you can draw this on your paper, on your exam, it's so easy. Notice here, let's say, I'll give you a big one. Let's see if I can, let's do potassium. Let's do potassium. I think potassium would be, yeah, potassium is big enough that we can do it. So I want you guys to understand this. So let's say potassium. Okay, so potassium is K, and it has no sign here. So that means it has 90. Oh, I actually want to do 2 things. So this is no charge. So let's see, no charge. So potassium, no charge. Oops, no charge. So that means it has 19 electrons, right? So if I ask you for the electron configuration, you're gonna start with 1s, 1s, and how many can you put in s? 2, okay? Then you go to 2s, 2s, 2. Keep counting how many electrons you have so far, 4. Then you go to p, 2p, 6. So you have 2, 4, you have 10 so far. Then you go to 3, 3s2. So you have 12. Then you go to P, 3P, so you have 3P6. And then you're gonna go to 4S, and you should have 4S1, right? So that's 12, 13, 14, 15, 16, 17, 18, 19. There you go. This is the electron configuration of potassium. If I ask you for the electron configuration of potassium plus, that means that it has 18 electrons. 18 electrons. So the electron configuration would be 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6. That's it. Notice the difference because this one you don't need it anymore. So knowing this diagram is really easy. So you just go, oops, sorry. You just number it. There you go. I just literally do 1, 2, 3, 4, 5, 6, 7. And then I start here. I don't do 1, I just do 2, 3, 4, 5, 6, 7. And then I start here, which would be 3, 4, 5, 6, 7. And then I just do this is S, 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 P, 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 D, 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 and then you do F. F, 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 F. And the trick is on the way you're gonna fill it. So you wanna go like this. And then you wanna go like this. Then like this. So notice the way I'm filling it. You wanna follow the arrows. See? And then you're gonna go to for D, for P, and for S. So that's the key. So if you can do that on your exam, you'll be okay. Now, each orbital holds a maximum of 2 electrons. When orbitals are equal in energy, 1 electron is added to each orbital until all the orbitals are half filled. Then the orbitals can be completely filled. So this is an orbital. We represent it on this little square. It's called the orbital diagram. This is an unpaired electron. This is a double electron. What they're saying is, if you have P, so in P, instead of doing the little square, you just do line. If you, let me do it too. 1, 2, 3. If you want to put 4 electrons, you first have to go up, fill the whole thing single, going up before you start doubling. If you do this, 1, 2, 3, 4, this is wrong because you have an empty orbital. These whole 3 orbitals on the P have the same energy level. So you want to put them singlet before you start doubling them. Notice here, so in orbital 1s, 1. That 1 indicates the electron. Helium 1s, 2. Here we have lithium, 1s1, 1s2. This is the electron configuration. This is the orbital notation. You need to know how to do both. Carbon, which is 6 electrons. This is the orbital. This is the electron configuration. Neon, orbital diagram, electron configuration. You need to know how to do both. Noble gases are the shorthand notation. So in order to do noble gases, you pretty much, in order to use the shorthand notation, you put in parentheses the noble gas that was before it. So for example, this is carbon, right? But this is, 1s2, it's helium. So instead of writing 1s2, we write the noble gas before it, and then we write the rest. So this is still carbon, but we didn't write 1s2, we just put helium. So it helps with the big elements that have a lot of electrons. It makes it easier instead of writing long notations. Notice here we have calcium. So this is the element. Here's the orbital diagram. Here's the electron configuration. But this electron configuration here is the same as argon, the noble gas. So instead of writing all of this, we just write in parentheses argon and 4s2, because if we see this, we know that this argon is going to represent 10, sorry, 12, 13, 14, 15, 16, 17, 18. We know that this is going to represent 18. We also have blocks. They call them blocks. So this everything in here, this is going to end up in S to the first, S to the second. This is going to be P1, P2, P3, P4, P5, P6, and then this is P6. So this is why they call this the P block. They call this the D block, and they call this the S block and the F block. Everything in here is gonna end up in F. It just makes it easier. You're learning, so I would say get used to the notation first and then use this block system. I have posted some videos for you guys to watch them and we can do some problems together. Okay, switching topics. This chapter covers so much. We're gonna be talking about valence electrons. Valence electrons are gonna be the ones on the outermost shell. So for example, on the last shell. The reason why these valence electrons are important is because those are the electrons that are going to contribute in a chemical reaction. Those are the ones that are gonna go into battle. They're called they call valence electrons. There are the electrons on the outermost shell. So for example, here, which one is the biggest shell? N2. So the valence electrons is gonna be everything on N2. In here for chlorine, which one is the highest? 3. So anything on 3 is valence electrons. So chlorine has 7 valence electrons. So in order for you to determine the valence electrons, you need to know how to do electron configuration. Elements in the same group have their similar electron configuration. So anything on group number 1, their electron configuration will be the same. Anything on group 2, the electron configuration will be the same. They have the same number of electrons. So anything on group 1 will have 1 valence electron. Anything on group 2 will have 2 valence electrons. Anything in group 7, with the exception of helium, helium has 2 valence electrons. Everything else will have a full octet. The chemical properties are going to be the same since they have the same valence electrons. Notice here, anything on group 8 is going to have 8 valence electrons, except with helium. Helium only has 2. Helium only has 2 valence electrons. Anything in group 7A is going to have 7 electrons. This is going to have 6, 5, 4, 3, 2, 1. But this is for the main group. Pay attention, anything with A. This is only for the main group, so it's important that you guys can be able to distinguish those. Sometimes we are going to represent those valence electrons with dots. It's called Lewis dot structure. So for example, we put 4 different dots around carbon because carbon has 4 valence electrons. We put 6 dots around oxygen because oxygen has 6 valence electrons. I'm gonna give you an example on how to write the ground state orbital diagram and electron configuration of magnesium. So how many electrons are magnesium? Magnesium has 14 electrons. So how will you write that electron configuration? You want to, so that means you need the S and the P. So 1S, 2S, 2P, 3S, and 3P. So you want to put the 12 electrons. 1, 2, 3, 4. Notice how I'm filling it. 5, 6, 7, 8, 9, 10, 11, 12. Then the electron configuration is this, and this is the shorthand notation. So stop it and try to do it by yourself. Here's another one. Now they're asking you for manganese. 25 electrons. This is something that you would do on your paper. And you start filling them. Here's the orbital notation. Here's the electron configuration. Here's another one. And here's the shorthand. Wait, did I do the same one? Yeah, I think it's the same one, sorry. Here is for potassium, which is 19. So you want to do the same thing. You want to pause it and you try to do it by yourself. Try to do the electrical configuration of those two by yourself. Here's the answers. Tin. Here's the answer. Selenium. Here's the answer. Magnesium. Okay. The next part of the chapter is just memorizing electron trends. One of them is being the atomic size, pretty much how big you go, or the radius, how you get in size as you go across the periodic table or as you go down the periodic table. So this is a trend that you have to remember. So for example, it says the size of atoms increases. So if you are here, if I'm comparing that one versus that, is going to increase, and it makes sense because you're gaining more electrons, so you're gonna become bigger. So as you go down the group, you're going to increase in size. As you go from the left to the right, you are going to decrease in size. The atomic radius is going to decrease. So questions that will be asked, something like this: which one is larger, potassium, lithium, sulfur or silicon, potassium or bromine? So you want to locate them on the periodic table. So in this case, potassium and lithium. So which one is further down? So this is further down. So in this case, potassium is going to be bigger because it's lower. First is lithium and then it's potassium. So obviously by that order, but because it increases as you go down. If you look at sulfur and silicon, in this case, silicon is going to be bigger because the atomic size decreases when you go from the left to the right. If you look at carbon and, calcium, and bromine, calcium will be the favorite one. So here are your answers. I also posted a video on this. The other trend that you have to know is the ionization energy, are also the definition, which is the energy removed to needed to remove an electron from an atom that is neutral. So something that is neutral, and you want to go and take an electron, how much energy do you need? Like if someone is at your house, like, you know, if someone is satisfied with their life, how much energy do you need to go rob them, right? Think of it that way. It's going to decrease as when you go down the group, but it's going to increase as you go across the periodic table. It's opposite of what we had on the atomic radius. It's the opposite. So you want to make sure that you know that it's the opposite, and you're going to be asked questions similar to that. Something like this. Which one is, identify the element in each pair that has the highest ionization number, means that's energy. So for the first one, notice that it's going to be lithium. The other one is going to be sulfur, and the third one should be bromine. Okay, so that brings us to the end. It's a lot of material, so please, I encourage you to take notes and ask me questions. I know it's a lot. This chapter is full of information, so we need to dissect it. But please, this lecture should only give you a general idea of the material. You need to try to attend our meeting so you can ask me questions. Okay, talk to you soon.